So, hello and welcome back to my C++ tutorial playlist. In the last video, we left off with a little cliffhanger. So we covered that this might lead to issues if the second object can't be allocated and there would be an exception, and then also T1 wouldn't be cleaned up. So what's the alternative here? And this is basically the use case for smart pointers, and they are in the memory header. So we need to include memory, not memory.h, memory. And then we wouldn't call new, we would call make unique, like so. And this would also then return a unique pointer. Because it's sometimes a little tedious to type, we can also just call auto here to automatically deduce the type. And then of course we don't need to delete anymore. And we can do the same thing for T2. And then of course we don't need to delete T2 anymore. And what unique pointer does is basically it takes ownership of a pointer that we create here and also constructs the object for us. So even if we throw something here, it would still be cleaned up correctly. I think we need to create a new function so we can see that it goes out of scope correctly. So let's see how that goes. We still need to catch the exception, as it looks like. But after that, we can see that even if we leave the function unregularly, we still call the destructor properly. And this wasn't the case with new. So let's just make a new example with new again. And then read T1, T2. And if you run this, then we can see that it won't be cleaned up properly. So this is the advantage of using smart pointers. And unique pointer is just the simplest form of a smart pointer. There's only one owner for a unique pointer. The unique pointer always has one owner. For example, T1 would be the owner of this newly created pointer here, and T2 of this newly created pointer. And when the owner goes out of scope, then the unique pointer would automatically call lead for us in the destructor, and likewise here. But what we can't do is we can't share ownership. For example, something like this won't work. We would have to explicitly move the ownership. So T1 loses the ownership and it gets then assigned to T2. But if we would have to have a shared ownership, well, it already has a shared pointer in C++, and we can construct that with make shared. And the shared pointer basically has a reference count inside of it. At this stage, it knows, okay, I have one owner. And then here at the copy assignment operator, it knows, okay, I have a second reference to me and I need to wait until two of my owners go out of scope until I can delete the resource I'm holding. So it will only delete itself after both owners are out of scope. And we can, let's see, well, we can run this example right here first, and we will see that one constructor is called and one destructor, as we can see here. But we can also avoid the destructor to be called by having the shared pointer of lifetime here, which is the T2. And then we would share the ownership with this one. So the destructor would only be called when this goes out of scope, but this never happens. So we would then see that the destructor is not called. 1 second. Of course, it goes out of scope when the program ends. So we can also check when it happens. Let's see again. As we can see, the lifetime was, the destructor was called after the exception happened. So after the program was basically done, after this function was already done, we went here and then the program ended and it cleaned up after that. As you can see, this is really interesting to play around with. We can also if we want to have a reference, but we don't want to keep the object alive, we can also have a weak pointer. This basically works the same way, but it doesn't increase the reference count inside of the shared pointer. So we don't keep the object alive. That means the lifetime object will be destroyed right here when we leave this function. And basically then afterwards the T1 reference would be invalid and we wouldn't be able to access it the object here anymore. Let's see. And as we can see, it didn't hold the object alive. We destroyed it before we went into our exception handling. So much for the lifetimes of the smart pointers. But now I want to remove all of this again. So we've taken a look at the lifetime of smart pointers. So now let's see how we can work with them. And for that, we will create a unique pointer type lifetime, and we call this one again and assign it to make unique like so. And we can still access the object underneath with the dereference operator like so. So you can work with them like with regular pointers. Of course, the lifetime object is a little bit boring, so let's maybe create a small struct, call it and it maybe has some data members x, y, and z like so. And if we then create object of blah, smart pointer to blah, of course, then here the tutu would be blah also. So we can access x, for example, through here and assign it and so on and so forth. Or we could, of course, directly access it through T1 with the arrow operator and also do assignments like so. Same would apply for member functions like hello. We could then of course use T1 to call hello, and yeah, we could also do this just like with regular pointers. So I want to now go over some guidelines. Basically, you usually don't ever want to call new, and that is for the reason that we have seen previously, that it can't guarantee that the resources will be cleaned up correctly. Even if you think you considered every case, it's really hard to keep track, and therefore you should prefer smart pointers. Of course, you can use raw pointers, and that is basically only the case raw when you don't want to own the underlying object. So raw pointers for non-owning and optional references. So a pointer could sometimes be invalid or a null pointer. If you want some reference to something that's always valid, then you should prefer references. Then second, you don't really want to create a lot of heap allocations anyway. So if you can avoid it, so instead of calling make unique, make shared or anything, you should prefer just create the object on the stack, like so for example, and then you don't run into these issues altogether, and it's also faster. Of course, this becomes a performance issue sometimes when the objects are too big or the stack might just be too small to store all the data. So that is something to keep in mind, but for a lot of cases, you really want to prefer the regular stack, and it's basically easier and faster. Then you might think, okay, if I don't want to use heap allocations that much, then I'm also limiting myself to use polymorphism, as we've seen in my video about inheritance, that you basically need a dynamic pointer. So to avoid that, you can basically use composition instead of inheritance. So you would have a data member that can get injected into you that holds the core functionality, so of your parent, for example, so to speak. So you really want to play around how you can avoid polymorphism, and that can happen in various ways. We can cover some examples of that in a later video when we take a look at sign patterns. And also, as we have seen, exceptions are a little bit tricky, so you want to avoid them also. And for that, we will take a look at STD expected in a future video. And also, memory management is sometimes a little bit tricky, even with smart pointers, and also slow, but you still might need it, especially for large objects. So you can think about custom memory manager or pooling system. This is often faster and safer when you have one system that handles all the complex stuff for you and you don't need to think about it anywhere else and just use that to construct your objects and destroy them. So these are some guidelines I want to leave you with in this video. We will take a look at each of them in more detail in some more practical context in the next videos. Or yeah, this is a little bit too much to cover all in one video. So and also I think it makes most sense to look at this in a practical context. So it makes sense why these guidelines, why I think these guidelines make sense. Thank you very much for watching again. I hope this has been helpful, and bear with me, we will cover these in more detail and in a more practical context in future videos. So maybe subscribe, and this might just be a fun homework to do to explore why these make sense and what the benefits of them are. Thank you very much for watching, and see you in the next video.